Do I sound okay? Seems a bit weird on my phone. Just normal? Okay. Just me then. So, what I'm going to do today is work on section 3.3, which is derivatives of trig functions. And I'll remind you that I said this yesterday as well, that these questions are not going to be in the homework, and they're not going to be obviously in the online. I'm going to mute everybody. I'm getting some good feedback. It could be me. So this will not be on the homework, will not be on the online test, and will not be in the midterm. But summer is so tight, we can't afford to tread water even for one day. So we're going to look at how to differentiate trig functions. These are the 6 trig ratios. In red, here are the derivatives. So the rules that you typically have already seen still apply. So if you were being asked to, say, differentiate 3 cosines plus 2 tans minus 4 cosecants, for example, it's really just referring to here. So a cosine gets you a negative sign, so 3 cosines would get you negative 3 sines, so that's all the multiples do. You want 2 tan x, a tan x gets you secant squared, so 2 tan x's will get you a secant squared x. And a cosecant x will get you this guy, so negative 4 of them, 2 negatives make a plus, you get plus 4 cosecant x, cotangent x. Now, the usual rules of style points apply. Does it look like the original? Yeah, it does. Can I factor anything? Nope. And if there's a trig identity floating about, can I use it? I think, again, the answer is no. So this answer is as good as it's ever going to get, which isn't very nice, but that's the answer. Now, you could have a function like e to the x sine x. Now, if you had this function to differentiate, I hope you would say, product rule. Seems pretty obvious. So the rules apply that 2 things multiply together. If you want to differentiate them, use the product rule, which is f dash g plus f of g dashed. And differentiate this guy, you get e to the x, leave this one alone, plus leave this one alone, and differentiate the sign. In this case, there is a little bit of style points, because at least I can factor out an e to the x. So as long as you know what the derivatives of these are, you treat them the same way you do all derivatives, right? If it's a product, you do a product rule. If it's a quotient, you should do a quotient rule. So let's see if we can do a sine x plus a cosine x over a sine x. Take away a cosine x. And no, you can't cancel the sines or the cosines, because these have a plus and this is a minus, and so these are not individual terms. They are a combination of 2, and factors can only be cancelled if they're identical. So let's move and see what the derivative is. I don't think it's a big surprise that this is going to be a quotient rule. Would you agree? It's kind of obvious. Fractions are obvious. Quotient rule. So its derivative is going to be f dash g, take away f of g dashed, all over g squared. Well, if you differentiate a sine x plus a cosine x, you will get a cosine x, take away a sine x. And then you leave the bottom alone. just that guy. And I wish I'd planned ahead because I now realise I need more room, so I'll rewrite it over here. Cosine x, take away sine x, sine x, take away cosine x. Subtract, leave the top alone, which is sine x plus cosine x, times g dashed. And if you differentiate this guy, you get cosine x plus sine x. And the whole thing is going to be over sine x, take away cosine x squared. So that's pretty ugly. So what I'm going to do now, well, I'm going to do style points. I'm going to multiply these two together and get a big horrible mess. Take away, multiply these two together, get an equally horrible mess. Collect like terms, hopefully get some things cancelling, then, you know, see what we get out of that. On the bottom, I'm going to do absolutely nothing. I'm just going to leave it alone. So on the bottom, I have sine x, take away cosine x squared. If you multiply this by this guy, what do you get? You get a sine x cosine x plus a sine x cosine x. I guess I should try and figure out how many cosine sines. You're going to get a sine and a sine. You're going to get two cosine x sine x's. You're going to get a negative sine squared x. You're going to get a negative cos squared x. Okay, take away. I think I'll do this separately. This guy, when you multiply it, you're going to get a sine squared x, 2 sine x cos x's, and you're going to get a cos squared x. Okay, so it's write them in kind of the order I like them. 2 sine x cosine x's. Anybody want to have a shot at what negative sine squared minus cos squared is equal to? Because it is equal to something by a trig identity, even if you're not. Say again?
-1.
Correct. Isn't sine squared plus cos squared 1? So negative sine squared, negative cos squared would be -1. Now, take away. Well, if you take this guy and this guy, don't you get 1? So that's take away 1. And then you're going to take away 2 sine x, cosine x's. And something really nice happened. Well, for starters, didn't these guys all become versions of 1? And then these two guys killed each other off. So the final answer ends up being -2 over sine x, take away cos squared x. Now, as far as style points go, this one is okay. Now, I know I said you should try and make it a fraction. You should try and not make it a fraction, right? So you never write things as 1 over cosine, you just call them secant, that kind of rule. That's true. But when it's something like this squared, there is no advantage, although technically it's still correct. There's no advantage to doing that, which it's not that much nicer looking. So this is okay. Any questions? It's really just, it's really just a matter of using these guys, isn't it? Product rule, quotient rule, whatever it might be. So let's try and make the life a little bit uglier. Here is a function that I would like to differentiate. Now, if you're thinking power rule, because that's quite a natural conclusion to make, you would be wrong. So I'm not going to add 1 to the power and divide by the new power and say that the answer is 1/3 sine cubed x. I know it seems quite reasonable, but it doesn't work. Sometimes you have to write something in a different form to understand how you're going to tackle it. Now that I've written sine squared x like that, can you see it's really a product rule question? Right? When it was written as sine squared, you were probably going to go down the wrong rabbit hole, right? You were going to think power rule or something, but it doesn't work. I mean, even if it sounds like it should, it doesn't work. So product rule it is. And so it's going to be f dash g plus f of g dashed. If you differentiate a sine, you get a cosine. Leave that one alone. Plus, leave this guy alone. And differentiate sine, you get cosine. So these two are actually both the same thing. So you have 2 sine x cosine x, which looks really nice according to the style point rules. But rule number 3 in style points is use trig identities, if there's one, to make it look even nicer. Does anybody recognize 2 sine x cosine x? It's a trig identity. What is it equal to? No takers? You remember it now? 2 sine x cosine x is the sine of 2x. So this would be considered the best form of that answer. What else can we try?
Wait, say that again. So 2 sine x cosine x
is equal to the sine of 2x. It's one of the trig identities that you would have learned, hopefully, you would have learned in trig. But let me show you some of the standard ones. I've already used this one today. Right? That's, if all the trig identities, that's one like everybody remembers, right? Sine squared plus cos squared is 1. There are some identities, such as this one. Where cos squared minus sine squared is a cosine of 2x. There's another version of that one, which looks like this. 2 cos squared x minus 1 is a cosine of 2x. There's a third version of that one. And there is the one I just used. These guys here are called the double angle identities. Double angle because the answer ends up being 2 x's. Do you recollect doing something like that, even if you can't recollect the specifics? Right? That's what makes trig so darn hard. There is a lot of identities, but these are very common ones, right? There'll be some weirder ones that you might not have seen, but will happen. For instance, just off the top of my head, what is sine x over cosine x?
It's tangent x, isn't
That's a
it?
tangent, yeah. So when you're on the derivative of a trig function and you've got all the good stuff done, right? You've got to whatever line you have this here. You should always be on like the last phase of the process, right? After you've factored everything, made it look like the original, done everything you could. You have one last look and you say, are there any trig identities in the thing I'm looking at? So if you're looking at this guy here, you're going to be thinking, I think I've seen that guy. Oh yeah, sine of 2x. You're done. Any questions? Are we good? Keith, if you've got a couple of minutes at the end, I saw your email and I can tell you what you need to know if you want to wait.
Okay, thank you.
Right, now, just picking one at random here. This is from homework that you're not going to be doing until next week. And we're using Thur because we can. That's F, that's G, pretty standard product rule. Nothing, don't think too surprising yet. Okay, when you differentiate a secant, you get a secant tan. So secant theta tan theta times another tan theta plus, leave this guy alone. And if you differentiate a tangent, you get secant squared theta. And well, let's tidy it up a little bit. Secant theta tan squared theta add secant cubed theta. Okay, so that's differentiation finished. Second phase would be like factor the heck out of it. Agreed? And they're not really much, but I hope you notice that there's a secant theta. Now, I really do wish that tan squared plus secant squared is 1, because that would simplify really well. But actually, tan squared theta plus secant squared theta isn't anything, right? There's no identity that it's equal to. It's just what it is. So actually, that's like question finished. Let's see, do version of question 10. F of theta is the sine of theta over 1 plus cosine of theta. Definitely a quotient, no? It's going to be f dash g, take away f of g dashed, all over g squared. You differentiate this guy, you get cosine theta, leave this guy alone. Take away, leave that guy alone. And if you differentiate a 1 plus cosine, you get a negative sign. All over that guy squared. Okay, differentiation has finished. I'm looking at this. I think that probably the best thing to do would be to distribute it first and then see, see what we have. Cosine times 1 is just cosine. Cosine times cosine is cosine squared. Negative sign times another negative sign is plus sines squared. Oh, you see a little 1 there, little identity. So what we have here is the cosine of theta plus 1 all over 1 plus the cosine of theta squared. You never know what you're going to get. And there's a big temptation for you to say, hey, I'm cool. I can see something I can do to this fraction. Do you see it? On the top, there's a cosine theta plus 1, which could also be written as 1 plus cosine theta, couldn't it? And do you notice that that's exactly who you've got in the bottom? So 1 for 1 cancel. And now I'm left with a 1 plus cosine theta. You can never take trig expressions for granted. You wouldn't have thought, or at least I wouldn't have thought, that this answer would have turned into that one when you saw what it looked like, I guess, on this line here, especially. Right? So you got to have a look. Now, at this point here, I should be saying, look, is there anything else I can do? And then I'm pretty happy to say, there's nothing I could ever do that would agree that's nice. And we did have a little trig identity as well, so it had that thing going for it. Try.
Professor,
Yes.
would it be feasible to do that as 1 + 1 over cosine to make it a little nicer, and then change the 1 over cosine to something else?
You're not allowed to split these two guys up. And that's because this is really a package. It's not 1 times cosine, it's 1 plus cosine. So that's not allowed.
Okay.
Now, well, you can't really do it the other way around, it'd be silly. You could do, imagine a different question. Like that question, right? Imagine you've got a fraction that looked like this guy. In this case, you could, if you wish to, that is splittable, if there is such a word as splittable, right? You can split that fraction. So not that way around, but yes, this way around. Now, if you did this one, you would get cosecant theta, and this guy would be cotangent theta. And yeah, that would probably be a nicer looking version of that one. But nope, that's pretty much as good as it's going to go. In fact, in a lot of ways, sometimes the thing you have to know is when to stop doing stuff or when to try and stop doing stuff. It's not always clear that you've reached the, you know, the ultimate version of good. Here's a quotient rule. Really nothing too surprising about the fact that it is a quotient rule. Okay. Probably need some room, so I'll do it over here. Okay, if you differentiate 1 plus secant, you get nothing, and then you get a secant tan. And then you leave this guy alone. Take away, you leave the top alone. And if you differentiate this guy, you get a negative secant tan. Multiply this out, which basically means foiling it all. Well, distribute, I should say. Secant tan. Don't know, somebody might. Everything should be a W, but for some reason I'm picking up X's through bad habits. So that's those. Negative this guy. Well, a negative of a negative makes it a positive. So you're going to get a positive secant W tan W. And that's a positive, that one. And so you get secant squared, I should say. Not a secant, done that. Then you get secant squared. It's pretty ugly. I haven't really looked yet to see if there's anything going on. Right, I have a secant tan here and I have a secant tan here. So that means I get 2 of them. And if I negative this guy and a plus that guy, so those cancel out. And that looks pretty good. Thinking of any identity that I know of? Nope, there's no identities I know of that would change the top row. And so on, calling it good. So let's do some special ones. Right. We did some like this yesterday, didn't we? Look at the situation that occasionally you might have three things to multiply rather than the typical two. So if I call this F, G, and H, and I can't remember who did it for us, but they said they remember it back in high school days. So here's the formula. It's F dash GH plus F G dash H plus F G H dash. Could you imagine that you could continue that for four things multiplied together? Or five things, not that you've ever seen them, but you could. So differentiate this guy, you get one, leave the other two things untouched. Leave the first guy untouched, differentiate the middle guy, leave the last guy untouched. Leave the first one and the second one untouched, and differentiate the last guy. Now, the only thing that I can see that they all share is e to the t. So that gives me a sine t, in this case, a t sine t, and in this case, a t cosine t. And there really isn't anything else you can do. We're finished. Let's do another group of questions that we typically do, and that is find the equation of a tangent line. And so the function that we're going to do is version 15, and it's y equals x plus sine x, and we're being asked to do it at the point pi pi. Okay, differentiate, you get 1, differentiate, you get cosine of x. The slope of the tangent line will be the derivative at pi, which is going to be 1 plus the cosine of pi. What number is the cosine of pi?
-1.
Yeah. And no, it is not a mistake that the slope is 0. It's a special case. If the tangent line is 0, doesn't it mean the tangent line is just going to be a horizontal line? Now, you could still use, and I'm going to disuse it to prove to you that it's possible, you could still use the point slope equation to do that, and it will tell you the answer. But you know that if it's a horizontal line, isn't it going to be y equals a number? And wouldn't you agree the number has to be the number that passes through this point? So it's going to be y equals pi. But for completeness sake, y take away y1 is x take away x1. I'm going to call that x1. I'm going to call this guy y1. And so it's going to be y take away pi equals 0, x take away pi. Well, 0 times anything is just 0. Now, did you see that it is what I said it was going to be? Right. Now, when we have a question like this, and it's one of the few times you can actually get something done about it, is that you should be able to just graph it as a check, right? So I'm going to put this into Desmos, and I'm going to put this into Desmos, and I better see a horizontal tangent line at the point pi pi, right? Let's go over to Desmos and see if what was predicted works. So it's y equals x plus sine x. Interesting shit. I'm interested in the point pi comma pi. You just type in pi for pi. And then I want to do y equals pi. Now this one looks like it's breaking the tangent rule, because shouldn't a tangent rule just touch the curve at a point and that's it? And unfortunately, this thing has a shape that's called a horizontal point of inflection. So what I'm going to have to do is I'm going to use the other feature of a tangent line. Would you agree if you scroll in close enough, the two things look like they're the same thing? Right. So it is not impossible for a tangent line to cut a graph, but it just at some other point, right? It can happen. Horizontal tangent lines are notorious for doing that if there's a horizontal point of inflection anywhere. So it did work. It was what it should have been. And I always like things when they do that. Any questions so far? Are we good? So give me a few moments to find where I was last time. Okay. I don't know, do I really need to do any more tangent lines? Like, do you know the process? Differentiate, put in the x coordinate of the point, and that tells you the slope, and then use the point slope equation, right, to do the rest. I'm just wondering, do I need to do any more of them? Are you comfortable with the process? Right? I can do one more if you want. Anybody, one way or the other? No great demand. So next thing we're going to do, which is pretty standard, is we're now going to find multiple derivatives. In other words, not just first derivatives, but first, second, maybe even third. So let's suppose I have a function e to the x sine x. Now, if I want to find its first derivative, it's going to be a product rule. So it's going to be f dash g plus f g dashed. So it's going to be e to the x times sine x plus e to the x times the derivative of that guy, which is cosine x. And now a little bit of style points, which is factor the heck out of it. And there's our first derivative. Now, if you want a second derivative, don't you just differentiate this guy, the first derivative? And this is also a product rule. And so it's going to be f dash g plus f of g dashed. So differentiate e to the x, you get e to the x, leave the g alone, plus leave the first guy alone, and differentiate this guy, which gets you cosine x to cosine x. Do you notice that both these terms share a common factor of e to the x? So I'm going to factor that out. And that means I'm going to have a sine x plus a cosine x plus a cosine x to cosine x. And that cancels with that guy. And I now have two of these. So I have 2 e to the x cosine x. And if I wanted, which I don't, but if I wanted a third derivative, wouldn't I just differentiate this? If I wanted a fourth derivative, I would differentiate whatever my third derivative was. And you could keep going forever. Sometimes with trig, and I suspect it, but I haven't tried it to be sure, that there might end up being a kind of pattern in the answer that you could use to predict the next derivative without actually doing it. So I've got a feeling, just a feeling, that if I did the third and then the fourth derivative, I've got a feeling that the fourth derivative would end up being a multiple of this guy. Probably 4. That would be my guess. but you'd have to do it. But if you notice that, and it's true, you can then say, oh, if you want the 202nd derivative, nobody in the right mind would, here is a shortcut, right? You've seen a pattern and you could do it. It's unlikely that you're going to get many situations where the pattern is so nice that you could do it, but it is possible. Now, this question, superficially, just looks like any other pretty standard quotient rule question. Find its derivative. In fact, this is going to be my last question for today, and then we'll talk a little bit about your midterm. The sky is F, the sky is G. I don't see anything too remarkable yet. And we're being asked to find its first derivative. So it's going to be F dash G, take away F of G dashed, all over G squared. Right, if you differentiate tan, you get secant squared X. And you leave that guy alone. Oops, that's a secant. You get a secant X. Take away tan X, take away 1. And G dashed gets you the derivative of secant. It's a secant tan. And this guy is over the bottom guy squared. So what do I have? I have a secant cube X. Take away this times this, so take away a secant X tan squared X. And that times that gives me a plus secant X tan X. All over secant squared X. Anything you can see here that we could do as far as style points to the top?
Pull out a secant X.
Okay. Now things are going to get a little bit less clear. Secant squared X, take away tan squared X. That is actually a trig identity. Secant squared X, take away tan squared X is equal to something. Any takers? Last chance, anybody?
Cosecant? No.
No, 1. It's equal to 1. So what I now have is a secant X, a 1 plus tan X, all over a secant squared X. And I guess I should have cancelled that earlier, but I'll do it now. And we've now got to 1 over tan X plus a secant squared X. So far, so good. Any questions? Now, style points. I haven't used this rule much, but it is there. Isn't there a rule that says if you can avoid a fraction, you should? In a lot of cases, you can, and that's fine. In this case, you can. Just rewrite the gap here. What is a secant x on the bottom the same thing as? In other words, what's 1 over secant x equal to?
Cosine.
Yeah. So what I now have is 1 plus tan x times a cosine x. And would you agree I don't have a fraction anymore? A secant on the bottom is the same as a cosine because 1 over secant is a cosine. Now, I'm now going to multiply through by cosine x, which doesn't seem to be a reasonable thing to do until you realize that tan x can be written as sine x over cosine x. And so this guy can cancel down. Now that shows you the power of trig identities, and it also shows you how darn ugly the process can be. The derivative of the original fraction ends up being that. And you can get much simpler than that. But wasn't there an awful lot of non-calculus to do that? It's all about manipulating trig identities. So you might want to keep adding trig identities as you find them. For instance, this one ends up being 1. Oh, I'm going to maybe use that again sometime. I better write it down somewhere. You're certainly going to use some of these as well. And that is all we need for that part of today. So what's going to be left with today, we're going to focus on your midterm. Just give me a few seconds there. While I'm doing this, you should probably do your last name for attendance. So I'm just getting the thing set up. Okay. Now I can tell you a little bit more than the first, on Monday when we talked about this. I can tell you a little bit more details about what your what your midterm, actually your final will look something like it as well, is going to be like. So here goes. It's going to be from 7 till 10 on Monday. You're going to use the link that is here. Where is it? That one there, the midterm exam. Oh, and wait a minute. I don't even know that you're actually seeing this. Right, you are, I'm assuming, there you go, going student here. Are you looking at my, our Canvas class? Right, okay. So, 1 hour early, set your alarm on Monday. Right. Your final, there I go and do it again, your midterm exam, which will look very like your final, will have the same format. It is not going to use any WebAssign at all. It's going to be all paper and pencil, PDF, just like you would do in a classroom. So the questions are going to look like that. There are going to be 30 questions in total, which sounds like a lot, which it is, but you should have plenty of time in 3 hours to do it. The first 10 questions are going to be multiple choice. So when I say multiple choice, I'm pretty sure you know what I mean, but let's make sure that we're all clear about it. Your first 10 questions are just going to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each question will have, A, B, C, D kind of choice, and you pick one. And for those questions, this is all I'm going to see. And if that happens to be the right answers, that is a sheer miracle. Just random, right? I will not see any working for the first 10 questions. So when you're doing your, photocopy of your working, you're just going to show me the answers to the first 10, the multiple choice. That's going to be section 1. And this is going to be worth 10 questions at 5 points each, which is going to give me 50 points. And then you're going to move on to section 2. Section 2 is also going to have 10 questions, and they're going to be worth on average 15 points, which is 150 points. So your midterm is going to be out of 200 points. Now in section 2, you will show me all the working you can possibly do. And one of the reasons you're going to show me all the working you can possibly do is if you make a mistake, you know, an arithmetic mistake, you drop a power of X, or you only get halfway through and then you can't figure out what to do, you can at least get partial credit. So if you got halfway through and where you got to was right, you're going to get half the points, right? If you did the whole question, but there was one arithmetic mistake, like it was 90% right, you're going to get 90% of the points. So that's the first, and that's a pretty important reason why I need to see all the working. The second reason I need to see all the working is you could simply just cheat. You could just go and find out the answer was 2x squared plus 1 and just write that down and tell me that you're really intelligent and you did all 15 lines of algebra in your head. And I'm going to say that's really good. And it's also worth 0 points because I can't see any work. So you're going to show me the working, because that's the way this game is going to get played. Now, that doesn't mean, and you probably will be using Desmos to check things, to find, you know, if you want to find out when something's 0, isn't it easier? You put it into Desmos and just find out where it crosses the x-axis, right? So things like that I won't see working for, because I don't expect to see working for things like that, right? But the good math stuff, right? The simplifying, the factoring, and all that good stuff, we do need to see them. If you're not sure if there's what kind of working I'm looking for in the Zoom lesson, you can just say I'm working in question 5, and I can't think of how to show you what I'm doing or whatever. And I'll say, well, you could simply just tell me whether you're using the limit as h tends to 0 or x tends to a, and do the answer that way. Right. Now we know, now that thought has came to me, you know that we have a shortcut for finding all derivatives, right? If I said to you differentiate 2x cubed, I hope you would tell me it was 6x squared, right? But if I ask you to prove it to me using the limit as h tends to 0 or x tends to a, do you see it's no good for you just to tell me it's 6x squared, right? There's a lot of math that has to be done there. Now, if I don't mention that you must use one of those two formula, that's really code for shortcut method, right? Product rule, quotient rule, power rule, whatever rule works, go ahead and do it. And what else? Chronological order. If you look at week 1, you'll get them from here. You look at look at yesterday, not today, because today had Trig in it, right? But if you look at yesterday's work, question 10 will be in that general area. And the same thing is true for section 2. You'll start off with the easy, well, not the easier stuff, but week 1 stuff, and you'll finish with week 3 stuff. Let's see what else. General advice: when you're doing multiple choice, if it takes you more than, say, 3 minutes to do it, you're doing it wrong. So pick C and move on. You can always put a little asterisk and change your mind later if you've got time. But don't spend 20 minutes on a multiple choice question. It's worth 5 points. It ain't worth a lot of points for you to spend a lot of time on. So just pick C or whatever your lucky letter of the alphabet is and go for it. In section 2, where working is necessary, you don't need to do the questions 1, then 2, then 3. You might want to, as a strategy, especially if you get nervous during exams, to do all the easy ones first, which just means the ones you know how to do. Just even if that's I do 7, 8, and 9, 10 first, because that's that's this week's work and it's fresh in my brain and I can do them. Then do them. We'll figure out. I can figure out where the answers are later. And if you have a question, especially in section 2, that you're just not comfortable with or sure what to do, that question should be your last question, right? Because if you've already done everything else, you should have a big chunk of points and you'll be psychologically in a better frame of mind when it comes to God, he's done one of those ones again. I hate those questions, right? At least you've got time to play with it and it won't be such a stress. Questions?
Professor, do we need to stay in the Zoom for the whole 3 hours?
No, if you're finished after 2 hours, you're going to upload your working. Let's do a little reminder of that. So 3 hours shouldn't, well, for some people it will, but for most of you, you shouldn't need 3 hours. So you'll be finished early. And as soon as you're finished, you leave. So let's suppose you've done your exam, you've written it all down, you're happy with what you've got. You then go upload your working, click on that one, upload file, choose file, pick the file, whatever you called it, and do it. Now you know that you have to use whatever software you like, but I've given you Microsoft Lens, right? You take pictures of your working. This software on your phone turns them into a PDF that you can upload, and you will submit assignment. But before you leave, you will say, I have uploaded my stuff and I will go and check. And I do simple things like I check all the answers are there, because I might say, you don't have question 4 or 5. And you're going to say, that's okay, I couldn't do those 2. And I'll say, that's fine. Or you'll say, oops, I kind of missed it when I was taking the pictures. And you'll go and do it again, and then you'll upload it, and I'll say, yep, everything is there. As soon as I say it's good, then you can leave. Right, I've checked it and there's nothing else to be done. And that will be it. Midnight Sunday, homework assignment 3 must be complete, no extensions. Online test 3 also has to be completed. There are never extensions to online tests. When you turn up on Monday, everything in WebAssign will have disappeared. You won't see it. And everything except the module that has all the information about the midterm will also have disappeared. So you got to make sure that you've got all the notes that you want already physically written down so that you're good to go. You are allowed to use anything that you've written down, any written notes. You're allowed to use Desmos. You're allowed to use your calculator, and you're allowed to use whatever's in your brain. Hopefully there's a lot of stuff in your brain. Okay, I like that question because it reminded me things I had to tell you. Any other questions?
I have another one. So I just look at the WebAssign and it shows that online test. Are we supposed to do the online test 3 first and do the trigonometry function?
The trig stuff should not even be visible anymore. If it
Okay.
is visible, I'll hide it. The trig stuff that we did today has nothing to do with the midterm, right? It's nothing to do with this week's work at all, right? It's just using that time so that we have so little time I have to use every minute we've got, right? So that's why the trig was there. It's not going to be in the test. It's not going to be in the online test or the midterm. So hopefully it's not visible, is it?
It's on the WebAssign.
Oh, well, I will make sure it's unvisible then if there is such a one before then, so you won't need to worry about it. Okay, any other questions?
Yeah, I might have misheard you, but it sounded like you said 30 total, but each section was only 10 questions.
Oh, yes, it's each section's only 10. I don't know why I said 30. I was
Ah.
probably thinking points or something.
Thank you.
So you heard me wrong. You heard me correct. I was wrong. It's 10 and 10. And, you know, the section twos do have an A, B, C in it. So, you know, they're not just one question. So I guess that might have been where my brain was thinking. But yeah, they're only 10 and 10. Your final is actually 10 and 20. So that might have explained something to me as well. Okay. I don't want your time's valuable. Is-
For the, oh, I have a question. Sorry.
No, keep going. As long as the questions, I'm happy. What you got?
So for the notes, I use my iPad for notes. Is it okay to use that?
Yes,
Oh, okay. Thank you.
it's really just notes.
Okay.
I mean, electronic notes and notes to me they're indistinguishable nowadays. Are we getting close to all the questions answered? Is everything do you think you know everything you need to know to do the midterm? Then